So let's look a little bit at derivatives here. All right, so all that a derivative is really is going to be the slope of a tangent line. You know, and you can really see that in how we typically denote a derivative, right? Like dy dx, change in y over change in x. You know, or also you've heard it. It describes a lot of things. The rate of change is probably one of the more practical ways to describe it. It's how fast is something changing at this one particular instance? Is it speeding up? Is it slowing down? Is it growing? Is it decreasing? So it's really a useful thing for us to be able to calculate. So real fast, let's look at a couple places where derivatives can't be calculated. I'll just draw a few little graphs here. All right, so the first one is if you have any sort of a corner. So let's say you have some kind of a graph that comes up and then back down like that. Well, at this point right here at the very top, there's gonna be no derivative, and likewise, if it's sort of similar, but if it goes like this, and then like right at those points here, now you could calculate a derivative up to that point, but on that particular point in general, so that's on these corners, there's not going to be you're not going to have a derivative. So also another place, well, let's just label this one for completeness. So another place that you're not going to have a derivative is if you have some kind of a function that comes up and then has a vertical line that goes up and then comes like that. Just because if you were writing your you know, if you were looking at, well, let's say you take this point right here, exactly where it's vertical. Well, your tangent line is going to be a line like that. And if you remember back to your algebra days, those lines, you know, those lines aren't necessarily possible because it's rise over run, but it's not running anywhere, right? So you're dividing by 0 in that case. So if you have one of these vertical lines, then that's no good. Last one we'll look at. Also, if your function is not continuous in any way, so let's say you come up and then you have a little break in the action there, and then your function goes on. Well, if it's not continuous, then you're also not going to have a derivative at that. And so that can look a number of different ways. This is just sort of one example. Again, you'll have derivatives all over the place, but just at that specific point, you won't have it. So with that, let's kind of visualize what these derivatives are, what exactly it is that we're doing here when we calculate this this derivative. So let's say that we have some kind of a function, just goes like this, whoop, kind of up. Okay, and then here we're gonna just kind of arbitrarily, let's call this point x, and that we're gonna have f of x. Right? And so we want to figure out how fast this is changing. So if we did that, then we could label some kind of value. We'll just call it h. All right. So if this is h right here, like in between, then this point right here is going to be x plus h. And then likewise here on our y part, we're going to have f of x plus h. So if we were going to take the slope between these 2 points, you just take your change in y over your change in x. So you're just going to have your f of x plus h, subtract your f of x, that's your rise, over your run, which is just going to be x plus h minus x. Well, we can simplify this a little bit, which we'll do in the next step. But before we do that, what we're going to do then is we're going to say, well, let's say, what if we took the limit as x, or I mean as h approaches 0? And so what we want to do is we want to say, well, let's make this just so small that it's going to grant us or going to give us wherever it would be instantaneously, boom, like at that one spot. So last but not least, one quick simplification. X plus h minus f of x. All right, down here in the denominator, we have x minus x, so that just leaves us with regular old h. So we're taking the limit as h approaches 0 of f of x plus h minus f of x over h. So real fast, before we look at an example of this, let me there's a real cool thing online that that kind of demonstrates this. So let's say you have well, let's bring this in just so wrong way. So let's say this is your h, how much you're moving from here to here. So you can see as we bring this in, like this is kind of, you know, maybe it approximates sort of how it's changing here on this curve, but not, you know, not really. But if you'll notice, what we're going to do is if we bring it smaller and smaller and smaller, the smaller our h gets, oops, there we go, let's put it right at like 2.04, right? So your h would be 0.04, right? And you see the closer that it gets to this point f, the more accurate it's going to be as far as being directly tangent to that one point. So that's really what we're doing here is we're taking this and we're moving it in whoop, to where it's so close that it's pretty much, see if I can get it to 2.01. Okay, that might be, no, close enough. All right. So that's really what we're doing with the derivatives. Same thing, you can take derivatives of, let's say, you know, this looks like we got x cubed, some kind of cube function here. So the same thing, boom, right? So really that's all that we're doing here when we take these derivatives. We're taking h, this change of it, and we're making it approach 0. So there's lots of really handy ways to do this. Let's work through this chapter. We're going to do a couple of hand calculations for it, but do not fear. It's one of those things that there's all sorts of equations that help you do these kinds of things easily. So this is one of those things that it's like, oh, this is really hard. Now let me show you the easy way in the next couple of chapters. But just for completeness, let's go ahead and we'll go through one example of how you would solve these by hand. So let me see. Let's say you want to take the derivative. Oops. Of 2x squared plus 4. Okay, so let's kind of start working through that. So if I want to take this derivative, then I'm going to first off use this equation right here, and I'm going to plug this in for it. So I'm only going to write this limit like one time or so because you know, we're going to do some other stuff. So just know that I'm writing this limit in my mind as we do this. So first we're going to do the function of f of x plus h. So what that means is every time I see an x in here, I'm not going to write x, I'm going to write x plus h. So I've got 2x plus h squared plus 4, and I'm just going to add some more parentheses around that, then minus 2x squared plus 4, because that's just f of x. So I've got f of x plus h minus f of x, all right, divided by h. Okay, so now this is just a little bit of algebra. So I'm going to FOIL this. So I've got 2x squared plus 2xh plus h squared. And if you kind of got lost in here, this is just FOIL. So first the two inner, outer and inner, and then the last. So from that, and then take this. So I'm gonna subtract 2x squared plus 4 all over h. Now let's get rid of these parentheses right here. Oops, and there's actually a parentheses around that. Because this is gonna have to distribute out there. Okay, so I'm gonna have, let's see if I can't write this whole thing, 2x squared plus 4xh plus 2h squared. I just distributed this 2 to that, and then also to that 4 plus 8, then minus 2x squared minus 4. Alright. All over h. So now we're going to start looking for things that we can cross out. So I've got a 2x squared minus 2x squared. I've got a, let's see, 4xh, can't do anything there. 2h, can't do anything there. Oh, whoops, you know what? I made a math error. This should be 4. I apologize. Because there's an in parentheses right there. So, but I do have a 4 minus 4, so that cancels out. So what I'm left with is 4xh plus 2h squared over h. All right, a couple more steps here. So with that, I say, well, I can take an h out. So I'm left with 4x here plus 2h on the top. Then on the bottom, I've got an h. There we go. So these h's cancel out. And I'm left with 4x plus 2h. And remember, this is the limit as h approaches 0. 4x plus 2h. Well, as h gets closer to 0, this just goes away. So therefore, I know that the derivative of 2x squared plus 4 is going to be just 4 times x. So that's the long way around. You can you see it takes a little bit of work, and it'll just this chapter will make us appreciate the next few chapters, because in that they give us just real quick ways to look at these and make derivatives real fast. So that's the basics of it, though. That should give you kind of a good start on it conceptually. And there we go.